Hello, I'm Dan, and this is Dan Explains. Have you ever heard of an eyeball planet? If you're watching this, you probably have. Modern thought on planetary formation predicts so-called eyeball planets are one of the most common planet types out there. However, I think they're rare if they exist at all. Let me explain why. Before we go into why eyeball planets probably don't exist, it'll help to understand what they are and why they are thought to exist and be so common. We're all very familiar with planets that are not eyeball planets, since none of the planets in our solar system are. This is an eyeball planet, or at least as close as I could get to one. According to modern theory, if our Earth was a star and the Moon had an atmosphere, it would be an eyeball planet like this. The feature that causes this is the fact that the Moon is tidally locked, which means we always see the same side all the time, because the Moon's day length is the same as its orbit around the Earth. The reason why tidal locking happens is revealed in its name, the tides. People try to make tides sound like free energy, and for us they pretty much are. However, the tides are generated from the gravity of the Moon and the Sun. The tides also affect the ground, squeezing the Earth like a rubber ball. They are just more noticeable in the oceans because they're softer than the ground. Now you'd think all this effect would do is just slow the orbit of the Moon. However, it's actually doing the opposite. The Earth is spinning faster than the Moon's orbit, so it's dragging the Moon faster and widening its orbit. To do this, it's slowing the rotation of the Earth. That's what causes tidal locking. Since the Earth is so big compared to the Moon, and the Moon used to be much closer to the Earth, the Moon experienced much stronger tidal forces, which rapidly slowed the Moon's rotation and widened its orbit at the same time, until it reached the point which minimized the tidal forces that the Moon experiences, which is a rotation that matches its orbit. This brings us to why these planets would be so common even though we have none in our solar system, although Mercury and Venus are pretty close to being tidally locked. Most of the stars in our galaxy are red dwarf stars similar in size to the planet Jupiter. Today, most of the planets we found around red dwarf stars have similar orbits around their respective stars as the orbits of Jupiter's moons have around Jupiter. If you didn't already know, you've probably already guessed, the extreme tidal force from the planet Jupiter has tidally locked all of its moons. Red dwarf stars have a similar effect on the planets that orbit close to them. That is, if the planet is large and stable enough and has an atmosphere. If that's the case, theory has it they turn into these eyeball planets. Eyeball planets look the way they do because one side always faces their parent star, and the other side remains in perpetual darkness. So, the star-facing side gets scorching hot, and the night side becomes frigidly cold. This temperature differential causes the air to flow from the day side to the night side in the upper atmosphere, which it then cools and falls and then flows back to the hot side nearer to the surface. There's a couple of major issues with this model, however. They're simulated in computers, and of course, things are a bit simplified. Most of the simulations don't take geography into account. Now, it might seem like it doesn't matter much, but consider water flowing down a bathtub drain. It doesn't just head straight for the drain. It creates a swirl. And no, the direction of the swirl doesn't depend on what hemisphere you're in. Coriolis forces of Earth's rotation are so small on the level of the tub that the direction of the swirl is determined by small imperfections in the surface of the tub, like the mountains on the surface of the planet. Of course, tons of images like mine here depict a swirl pattern in the clouds. However, planets aren't tubs. The geography is going to cause more resistance to the airflow in some directions than others. Once the air flows from the day side to the night side, it's still going to have momentum. It's going to be more energetically favorable for it to just keep going, rather than turning around like is regularly depicted in an eyeball world. What you end up with, instead of an eyeball world, is what's called a super rotator. We actually have at least one of these, maybe even two of them, in our solar system. Venus is a super rotator. Its clouds race around the planet every 24 hours. Well, the planet takes 225 days to rotate. The sun at the equator is more intense than at the poles, so the winds there are faster, which is why the clouds are these weird chevron shapes depicted in this awesome ultraviolet photograph taken by Kevin M. Gill. Venus rotates, of course, even though it's very slow, so the rotational forces take over, causing this west to east airflow. In the absence of rotational forces, the air would flow more like it does with the tub drain. It would naturally find a direction which reduced its interaction with the mountain ranges. So basically the wind would run parallel with mountain ranges. We missed something though, and that's the thing I think most people miss. Sure, the planet is always facing its star, but it is still rotating. In fact, in many cases, they're rotating much faster than even Venus, or the Earth. Consider this. There are planets with years that are less than our 24-hour day. Even if the planet is tidally locked, it's actually rotating even faster than the Earth, since they are so close to their parent star. Rotational forces aren't an effect of the parent star, they're just an effect that arises from a body spinning in free space. What that means is these tidally locked worlds, orbiting close to their parent stars, are actually experiencing pretty substantial rotational forces. So, they'd probably end up being super rotators like Venus. If they were life-sustaining worlds, this would actually probably be a good thing, since superrotation helps more evenly distribute temperature around the planet, depending on how thick the atmosphere is. So, life-sustaining worlds around red dwarfs would probably look more like this rather than this. This of course glosses over the fact that red dwarfs make mostly infrared radiation, of course, so the planets would most likely look white or cyan to us, since they would most probably reject most of the visible solar radiation that we see, with maybe the exception of red, which is why they may look cyan. Their life would probably also be damaged by our light as well, since their chemistry wouldn't need the strong chemical bonds we need to resist being broken apart by our higher energy light on Earth. The irony here is, they would most likely need to be highly resistant to radiation overall, because red dwarfs are very active and are usually flare stars. Anyway, that's a bit of a tangent. The result of all this is the traditional eyeball world, close to its parent red dwarf star, that planetary scientists usually imagine doesn't actually exist. That's not to say that eyeball worlds don't exist at all. You could have cases where a planet is far from a larger star like ours, but rotates in sync with its parent star by some odd event like Venus almost does. Although, even in this case, you would have a superrotator like the first one I described, where the atmosphere superrotates in a direction to minimize the friction with surface features, like water does while swirling down a bathtub drain. Although in super rare cases, where you have a very smooth planet, like an ocean world for instance, that is far from its parent star, but also by some coincidence rotates exactly in sync with its parent star, you could have an eyeball world. So, it's not impossible, but probably much more rare and not found in the places previously anticipated. Thank you for watching. If you like this video, please press the like button. Subscribe to my channel and ding the bell to get notified when I post new videos. Also, please support me on Patreon, link in the description. The more people support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.